This time, we will look at the output mode of the 16-bit timer counter as the fifth content in Chapter 6, Timer Counter. Chapter 6 Timer Counter consists of the contents as you can see. This time, we will look at the output mode of the 16-bit timer counter. Let's first look at the normal mode among the output modes of the 16-bit timer counter. Normal mode is the simplest mode for the timer count 1 as it always operates as an up counter. An overflow of timer counter 1 occurs when the TOV flag is set. When the TCNT1 value changes from 0xFFFF to 0x0000 and an interrupt occurs. So as you can see, if you check timer 1 overflow in the interface and set the value to a specific value, the count starts from this value and an overflow interrupt occurs. So the initial value of TCNT can be set to a value other than 0. If we set the same value every time an overflow interrupt occurs, we can set it so that the interrupt occurs every cycle of the required period. If you give 16 MHz ATmega128 TCCR180X00 and TCCR1B0X02, division by 8 will be set in this state. If the TCNT1 value is given as 63,536, it is 0xF830 in hexadecimal. And since we need to overflow timer count 1, let's assume that we set the TIMSC value to 04. In this case, the value of the period is 1 divided by 16 microseconds times 8 times 65,536 minus 63,536, resulting in a period of 1 millisecond. As you can see, the overflow interrupt of timer counter 1 is called every 1 millisecond. So, in order to continuously generate an interrupt every 1 millisecond, we need to give 63,536 to TCNT1 as you can see. So as you can see, first shift 0xF830 from high to low bit by 8 bits and record it. After that, you can immediately record the lower 8 bits in TCNT1L. The specific period calculation formula is, as you can see, it's like this. You can calculate this equation yourself using a scientific calculator, so we get 1 millisecond. Up to this point, we have looked at normal mode. This time, we will look at CTC mode in timer counter 1 or 3. Mode 4 and Mode 12 will be the corresponding CTC modes. So, Mode 4 will be OCRNA and Mode 12 will be ICRN. Therefore, the TCNT value increases up to each comparison match value, and a match may occur at the moment the TCNT value becomes 0x0000. So as you can see, when two comparison matches occur like this, we can send out one output waveform. Therefore, OCRNA and ICRN can be used to define the top value for the TCNT value. In Mode 4, OCRNA is used as the top value. And if the TCNT value matches the OCRNA value, OCFNA is set and an output comparison interrupt occurs. In Mode 12, the ICRN value is used as the top value. And when the TCNT value matches ICFN is set and an input capture interrupt occurs. This time, if the CTC mode is set to toggle in the output mode waveform, the toggle value will be continuously output through the OCNA pin. This happens whenever the TCNT value matches the top value. So, the formula for calculating the period of the output waveform is as you can see. So, since we need to know the OCR value to create a specific frequency in this equation, the equation must be developed as you can see. So, you should know that this formula is provided in the Excel file. I provide as explained in the 8-bit timer counter CTC mode. We will continue to explain CTC mode. CTC mode can be at its maximum frequency when the top value becomes 0. Also, if you want the output waveform to be output through the OCNA pin, you must set the input-output direction so that it is output. And the TOVN flag is set and an interrupt occurs. What is this case? This occurs at the moment the TCNT value changes from 0xFFFF to 0x0000. Now I have explained the CTC mode to this point. Let's take a look at the third 16-bit timer counter output mode. Fast pulse width, modulation mode, fast PWM mode. This fast PWM mode has modes 5, 6, 7, 14, and 15. And fast PWM mode can be useful for generating PWM waveforms corresponding to high frequencies. In this mode, the TCNT value increases from 0 to top, then goes from top to 0, and then increases again to top. Therefore, as you can see, the top value can be set to such as 8 bits, 9 bits, 10 bits ICRN and OCRNA. So, look at the waveform generation picture to understand the principle of waveform generation. It starts from 0 and is cleared when it matches the OCN value. When it reaches the top value and changes to 0, it becomes set. That's what this explanation is about here. So, in the non-inverted comparison match output, the TCNT value increases, and when it matches OCRNX, a value of 0 is output to the OCNX pin. And the fourth explanation is that the moment the TCNT value becomes 0x00001 is output to the output. If we use the inversion mode, This output will be output with the opposite logic value. As you can see, the TCNT value increases, becomes set the moment it meets the OCRNX value, and becomes clear the moment it changes from top to 0x0000. We will continue to explain fast PWM mode. This fast PWM will determine the output period to the OCRNX pin according to the value set as the top value. The high and low part of the pulse width are determined according to the OCRNX register value. The PWM waveform will be output. The period calculation formula is as follows. When the output waveform is output to the OCRNX pin, the pin corresponding to the data direction register must be set to output. In this mode, when the value of TCNT matches the top value, the overflow interrupt flag TOVN is set and an interrupt is requested. Depending on the register used as top, the corresponding interrupt may be requested when the OCFNX or ICFN flag bit is set. If we set the toggle mode in mode 15, using OCRNA as the top value, we can get a square waveform in the output mode with a ratio of 50%. This concludes the explanation of fast PWM mode. This time, I will explain phase correct PWM as the fourth content. This mode corresponds to modes 1, 2, 3, 10, and 11. It can be useful for generating high-resolution PWM waveforms. This mode will be such an operating counter that the TCNT value has a dual slope where the value increases from 0 to the top and then decreases back to 0. As you can see, the top values are 8 bits, 9 bits, 10 bits, ICRN and OCRNA. Therefore, as you can see, increments and decrement occur like this. So, clearing occurs during increment. During a decrement, a set occurs. And the inversion mode will output the opposite logic that I just explained. This will be numbers 4 and 5 that I just explained. So once again, while the counter is incrementing upward, clearing occurs when it matches the OC value. Please be aware that a set occurs during a downward counter or decrement. We will continue to explain the phase correct PWM mode. In this mode, the output cycle to the OCNX pin is determined according to the value set to top. The pulse period is determined. The high and low part of the pulse width are determined according to the value set in the OCRNX register. The PWM waveform will be output. The calculation formula for the output waveform is as follows. In phase-correct PWM mode, the frequency will be reduced by half compared to fast PWM mode. In order for a waveform to be output to the OCNX pin, the data input and output directions of the pin must be output. Up to this point, we have explained the phase-correct PWM mode. This time we will look at the phase and frequency correct PWM mode for the fifth time. This mode is useful for generating high-resolution PWM waveforms, such as phase-correct PWM mode. There are modes 8 and 9 here. In this mode, the TCNT value increases from 0 to top during counter operation, and then decreases to 0 again. The applicable top value can be set by ICRN and OCRNA. This mode is similar to phase-correct PWM mode, but has differences. The point at which the register value set as the top value is updated is that in phase-correct PWM mode, TCNT is updated at top, and in phase and frequency-correct PWM mode, it is updated at 0x0000. We will continue to explain the phase and frequency-correct PWM mode in non-inverting mode if an operation in which the TCNT value matches OCNX occurs during upcount, clears output through the OCNX pin. If a match occurs during the downcount, a set will be output. In inverted comparison output mode, a logic value opposite to the output described above is output through the OCNX pin. Depending on the value set to top, the high and low part of the pulse width will vary and a PWM waveform will be output. The formula for calculating the period of the output waveform is as follows. I hope you know. Above, we have explained the phase and frequency correct PWM mode. This is the sixth content in the 16-bit timer counter output mode. Let's take a look at input capture units. We need to store the control values in the ICR input capture registers of timer counters 1 and 3. At this time, we can receive the value using the function of capturing the timer counter N. As you can see, it can be taken from an analog comparator, or the value with optimal resolution can be directly written to ICPN through software. We will directly calculate and write the optimal resolution value in the ICPN register. Please note the operation of this process, which is received through an analog comparator as a reference. This time, as the seventh content, I will explain the output comparison units. applies to timer counter 1 or 3. As shown in the following picture. The key point of this figure is that the register TCNTN and the output comparison register OCR and X are continuously compared to produce output. If TCNTN and OCR and X match, and the OCFNX flag bit is set, an interrupt will be requested. The output waveform is output through the OCNX pin. Please note that the waveform output at this time is set according to the mode. Determined from WGM 3 to bit 0. So, you should know that output is output to the OCNX pin by bits WGM 3, 0 COMNX 1, 0. This time we will finally look at output comparison modulation. Output comparison modulation is a function that is created by modulating the waveform and refers to having a comparison match. To do this, we use the output pins of OC1C, timer counter 1, which is a 16-bit timer counter, and OC2, which is an 8-bit timer counter. For output comparison modulation, if activated, 2 output comparison channels will be modulated. As you can see, if OC1C of timer counter 1 and OC2 of timer counter 2 are simultaneously output to pin 7 of PRTB, modulation occurs. Therefore, as you can see, port bit 7 must continuously use the output of OC1C and OC2. They must be used simultaneously. They must all be output at the same time. Both OC1C and OC2 must be set to output comparison match, and the output comparison value must be output to this pin. OC1C and OC2 must be activated at the same time. Modulation will automatically be activated by the output coupled to OC1C and OC2 and the waveform of the modulation. To achieve this, pin 7 of PRTB must be activated as an output. Next, we will continue to explain output comparison modulation. This first explanation is explained through the following output waveform picture. System clock is coming in. We assume that the output to OC1C of timer counter 1 is generated using fast PWM mode as follows. Also, assume that timer counter 2 outputs to OC2 in CTC mode as follows. If pin 7 of PRTB is set to 0, the waveform of OC2 is masked by the low of OC1C, and the final waveform is created and output. If you set the value of PRTB to 1, the high part of OCR1C masks the OC2 part and outputs the low part of OC2, as is, resulting in a waveform like this. So as you can see from the modulated waveform, please be aware that the output varies depending on whether bit 7 of PORTB is 0 or 1. So far we have looked at all 16-bit output modes of the timer counter. Thank you.